Thank you very much, Alan. Thank you, everyone, for being here. It is a real pleasure to be starting this presentation with what we are doing at the Australian Astronomical Observatory. So I'm a research astronomer at the Australian Astronomical Observatory at Macquarie University. So let me first show you that the majority of the information that we get from the stars, from the universe, it is coming in the light. But to observe that light, we actually have to dim our light. We need the darkness of some places just do not have light pollution at all in order that we can see the very faint light from the stars and very faint and distant galaxies. So if you can please dim the light a bit from here, hello, dim the light, you will be able to see much better what I'm trying to tell you today. So that is our Milky Way, our galaxy, seen from Sidon Spring Observatory, which is where the Anglo-Australian Telescope and some few other telescopes at ANU, the Australian National University, are located. That is the huge dome of the largest optical telescope in Australia, the Anglo-Australian Telescope, 4-meter telescope. We want to understand what is happening with the light of the stars. For doing that, we need to collect the light. So astronomy is very different to other science in that sense. So we do not do experiments. Well, we do some the simulation that Luke will be talking later. But we have to be collecting the light patiently and taking the light in order that we can detect this faint thing. But the main important part in astronomy, again, they are the stars. So that is the sun. It is an image of our sun. I want to emphasize as a star, it is just a giant kitchen. It is just, you have hydrogen and you are creating other elements. So it is creating for hydrogen into helium. But I'm not going to talk about that today. I just want to show you the comparison of our sun, which is 700,000 kilometers wide, with the Earth. And you may think that the sun, it is big, and it is big for us. But it is actually not that big when we compare with other stars in the universe. So if we put the sun in that kind of a scale, there are other stars that are much larger than the sun, much bigger. There are blue stars, supergiant red stars, and a plethora of many different kinds of stars, even very dwarf, faint red stars. So the funny thing here that we astronomers were able to understand during the last century is that we can organize this in a very nice way. So we have the brightness in the vertical axis and the color in the horizontal axis, and there is some kind of evolution and sequence. So we have brightest blue objects that are very hot, while the red objects are very, very cold. So just using colors and using the brightness, we can actually start understanding and collecting the data to what stars are. And galaxies are collections of millions, of hundreds, thousands of millions billions of stars. Some of them are elliptical galaxies in the sense that we only see a kind of elliptoid shape, red colors, meaning that they are all stars, the majority of them, while other galaxies, such as spiral galaxies, they usually tend to have these blue colors, and blue colors are revealing the giant stars. So we can put that in context in data and say that a file containing just the brightness and the colors of one star of one galaxy, it is only 100 bytes. So it is not that much. So not that much. With a DVD, which is the scale that I'm going to use for you today, 4.4 gigabytes, a DVD of data will have the information of 47.3 million objects. But that is only just collecting the colors and the luminosities. We are going to go deeper because let me show you another important thing in spiral galaxies. All these red colors that you see here, they are actually star-forming regions. They are nebula in that galaxy in M74. So we have an example here of the Eagle Nebula, and the light coming off also from the nebula, it is very important for us. And I want to say that the light is actually, the gas is actually growing because of the effect of the massive stars. So these stars have been born inside the nebula. that is just using an image. If the red color, it is coming basically for the hydrogen, which is a diffuse gas within galaxies. We can use special filters to see the nebulas and the galaxies in a different way. For example, it's here, and it is just a completely different way of understanding the universe. So if we actually go deeper into the detail, we need more than colors. We actually have to analyze very carefully the light coming from stars, galaxies, and nebula. Imagine that a star. If you take the light of that star and you use a prism and you get the rainbow, all the colors of the rainbow, you actually have something that the astronomers and physicists call the spectrum of the star, or the spectrum of a galaxy. And if you put here a lens and you get the information there, you will see that it is not a continuum of the light. There are some black lines, a code bar in the light coming from stars and from galaxies, and these are related to the chemical elements within those stars and within those galaxies. So codifying all those lines, codifying all those absorptions of elements, it is also very important in order that we do the physics and we try to understand what is happening in galaxies and stars. So that is what is happening. I mean, that is when we use a star. That is the kind of light spectra that we have. But for a nebula, that is a very different thing. As I told you, the light of the gas is actually emitting a lot of light, but emitting light in very particular lines that are the emission lines. For example, that one, this bright one, it is oxygen, and that is why you are seeing with these special filters, with these special images, you are seeing the colors so nicely. Of course, we astronomers, we do not want to see this very nice image. We tend to do something like this. Don't be scared. Don't be scared. It is just a cat saying, well, the color or the wavelength, which is the physical property, and in the vertical axis, the flux, how much intensity you have. So we have all these lines of hydrogen, helium, sulfur, oxygen, iron, just name it. And that's the way we know the composition, the chemical composition of stars and galaxies, even though they are very, very far away. So what we have been doing for a lot of time, at least until the late 90s. So we have the field of galaxies. Right? We'll go take the spectra of the galaxy, be there collecting light for 20 minutes, half an hour, and with that, we have a look to all these lines, emission and absorption from stars and galaxies, and we can determine the distance where the galaxy is, how many young stars, how many old stars, the chemical composition, the age, plenty of more information that I'm not going to go into detail. But just a single of these spectra will have 200 kilobytes per galaxy. Imagine that we are doing that during a lot of time for just taking your telescope, pointing there, taking the light, go to another galaxy, and so on. That is what we were doing till the 90s, and we get around 10,000, sorry for that, around 10,000 galaxies. But Australia and the Australian Astronomical Observatory have developed really powerful instruments that are able to do much better. That is the 2 degrees field, or the 2DF instrument at the 3.9 meters Anglo-Australian telescope, which is just a plate more or less this size. And in that plate, you can put 400 optical fibers in the position you want in order that you can observe at the same time 400 objects in the sky. So typically, we observe 360 galaxies at the same time. So in a good winter night, we can get even 3,000 objects in a single night. That means that in only 4 nights, 2DF is able to observe the 10,000 galaxies that I told you that took decades for other telescopes to get. Thanks to that was commissioned at the end of the last century. We completed the 2DF Galaxy Redshift Survey, 2DF GRS, in 2002, and that is the actual three-dimensional distribution of galaxies far away that you can see in the diffuse large scale of the universe, how they are connected by filaments and some condensation of galaxies. And that was the depth of 2.5 billion light years with 230,000 galaxies. So that data was only 44 gigabytes of data, or equivalent to around 10 DVDs. But we are just starting, because After that, we have been completing more surveys, that most of these optical surveys go even deeper and deeper in the universe. That is one of the most important ones, the gamma survey, the galaxy and mass assembly at the AAT. So we completed, it was completed in 2013, more than 300,000 galaxies observed. That is again a distribution about a very particular part of the field of gamma, the 5 gamma fields. And we use actually a new spectrograph, a new thing. So we were getting a megabyte per galaxy. So that were at the end around 71 DVDs just to contain the information that we got of all these galaxies. 2DF, this very interesting instrument at the AAT, can be not only used for galaxies. We have been also using that for stars. But for stars, we actually need a bit better resolution, and that is why we built the Hermes spectrograph. And we are now conducting the galactic archaeology with Hermes, the GALA. Here you see the GALAs observing at the Anglo-Australian telescope. That again, the aim is to get around 1 million stars in the Milky Way and in the Magellanic Clouds, just trying to understand the revolution and how the galaxy, our galaxy, the Milky Way, have been assembled. So just that, around 2 megabytes per star, so equivalent to 442 DVDs. And we are going there, still telling you, because that is okay for galaxies. So we are taking just a spectrum of a galaxy, but if you see an image like this, M51, the Whirlpool galaxy, and you put and try to get the spectra of just getting one particular position of the light, well, that is not the galaxy. So you can go to the center, you can go to the other one, to another H2, the other star-forming region. So we actually need new instruments to go deeper into the understanding of the galaxies. And that is why we have developed in the last decade this kind of structure that it is actually not taking a single spectra of one galaxy. It is taking hundreds, thousands of spectra of galaxies. And it is called the technique integral field spectroscopy because it is just doing the integral field. And it is much better seen perhaps with this image in which at the end what we are not collecting, we are not getting, it is just a spectra. We are getting cubes of data. And it is very, very, very interesting just to try to see moving around those cubes and trying to get the visualization of all of that because it is really tricky and it has we need a lot of computer power. So we have 10 to 1,000 spectra per galaxies. Perhaps the very first survey doing something like that was the Khalifa survey, which we conducted in Spain with a Spanish telescope. And around 500 megabytes per galaxy, 700 galaxies. So at the time, we only have 78 DVDs. Well, again, you go to your galaxy, put your instrument there, and just wait and collect the data for several hours. We need to do something a bit more better. And that is, again, why we are pushing the technology. And we at the AAO and with the Sydney University, we have built this new instrument, which is called SAMI, the Sydney AAO Multi-IFS survey, that we are not only getting the data in that way for one galaxy, but for 13 galaxies at the same time. And every one of these have this kind of bundle, and with the spectral field of the galaxy. Every one with 51. That is me at the telescope just a few months ago, actually doing this because the thing is that we have to do it manually. It is the thing. But we have already 1,800 galaxies observed. We aim to get 3,000 galaxies, and we will get 22,326 DVDs. And I think that wait for it. And I think that wait for it because at the same time the AAO is developing the Taipan survey to be installed now in August, September at 1.2 meters UK Smith telescope in Silent Spring, and that has the system that is called Starbucks. And these Starbucks are actually moving around, and it is you do not have to go and plug. It is just a computer that is able to move and put everything together in just some few 30, 40 seconds. I'm not going to give you too many details about that. It's going to do stars and galaxies at the same time, and we are going to get around 666 DVDs because they are just fibers. It is just testing what we really want to build, which is Hector at the AAT, which is just a system that is able, where it is coming, please? that we want to observe 100,000 galaxies using the bundles, and then we will get only for one galaxy 5 gigabytes of data. So that will be the equivalent to 113,636 DVDs. What do you think? Come on. Wow. We go directly into the Star Wars, I mean, into the galaxies. We will get unprecedented statistics for understanding the galaxy's properties in the local universe. And let me just give you this last number for finish. Just the AO telescopes have provided 1/3 of all the redshift of the galaxies that the humanity has right now. And that has been thanks to the technology and to the astronomers that we have at the Australian Astronomical Observatory. Thank you very much.